Hello, good evening, or good morning, or good afternoon, wherever you are in the world. Welcome to our research seminar. It's lovely to see so many of you here and to see in the chat all the different places that people are joining from. So my name is Catherine Childs. I'm part of the research team here at the Raspberry Pi Foundation, and I'll be chairing today's seminar. So this is our fifth seminar in the series that we've been running on cross-disciplinary computing. And the aim of this series is to really explore some of the intersections that you have between computing and other subjects, and thinking about what computing education looks like across different contexts. So all that being said, I'm going to move on now and introduce our speaker for the seminar today. I'm absolutely delighted to be able to do this. I feel like this is a real privilege. So I'm welcoming today to our seminar Conrad Wolfram. Conrad is a physicist, a mathematician, and a technologist. He's strategic director and he's European co-founder and CEO of Wolfram Research. His latest publication in 2020 is a book called The Maths Fix. And this argues that maths education was failing to address the needs of learners and society in the age of AI, and calls for a rethink on how we should do this. The title of his talk today, as you can see on screen, is around building tomorrow's core computational curriculum. And we're delighted that Conrad is going to outline for us his team's decade of work that they've done, mapping out a computational curriculum that aims to transform computational literacy. So Conrad, if you're ready, we'll stop sharing our slides and we'll hand over the next 40 or so minutes to you.
Great. Well, thanks very much indeed. Thanks for the invitation to be here. Nice to see you all. And I hadn't realized quite how international a group this is. So that's nice to have. And thanks very much for the kind introduction as well. As Catherine said, what I really want to talk about is stepping back from the day-to-day of what we've been doing in coding or in maths or in STEM, and trying to just understand, we've got some central subjects here. What is it we ought to be doing from a curriculum point of view? And how is that different and addresses some of the challenges that we have today? And so I kind of want to, I'm going to dot between things I've learned in my day job and, in a sense, what we've been doing from an educational point of view. So I think most of this, I'm just going to start sharing my screen. Hopefully this will work correctly, like so. So you should now see the title of the talk and, my sort of sub thing here, which is integrating coding, maths, and STEM for the AI age. So I think what I'd like to do is sort of, in a sense, start the story here from, my day job and how I came into doing this. So my day job has been for just over 30 years now to help to build computation into ever more potent force in the world in terms of providing computing and the ultimate, we're trying to do is build the ultimate computational language with Wolfram language that tries to put together all the algorithms in a sort of very coherent way so that we can really empower people to have the best machinery with which to do computation. That's, we want to build the best machinery to make it as easy as possible for all levels of people to deploy this fantastic process of computation onto decisions they have to take, onto problems they're trying to solve. And obviously that's given me a certain insight into how the world uses math and computation and coding and through Mathematica and WolframAlpha. And that's sort of what I have started to learn needs to be brought to bear on our educational system. So sort of potted history, Mathematica was released actually in, it was started to be built in 87, it was released in 88. Funnily enough, we discovered when WolframAlpha was around that 23rd of June when it was released was actually Alan Turing's birthday as well, but that was a coincidence with its release. And actually, Steve Jobs was at the release event and came up with the name Mathematica because it was bundled on his Next machines, as they then were, which is kind of cool. And so that's how it came to be called Mathematica originally. And I think that the interesting story here is how over the 33 years, originally we were kind of a niche, you know, in the sense that mathematics was somewhat niche. You know, we were in research departments, we were in universities. But what's happened over those 33 years is mathematics, or call it computation, is everywhere. If you're in the board of a company, a major company, you're worrying about computation, maybe in the form of data science, or maybe in the form of getting the right code written or whatever, but you're worrying about that. That never happened 30 plus years ago. And so we've been sort of, as I put this sort of thing, we've been pushing that. We've also been the beneficiaries of that. It's been a sort of iterative process, along with others, of course, in the field. And I think that's very exciting. We're part of a crest that I think is yet to fully form. And I'll stick this in for later discussion, but I think there is a parallel between computation now and the rise of electricity. We're perhaps somewhere in, you know, the 1860s or something with respect to the development of electricity. So my day job is, as I said, computation for everyone. We want to build the best machinery. It's as smart as possible so that it deploys everyone at every level to be able to deploy that on what they're doing as well as possible. And my sort of evening job, so to speak, for the last, I don't know, 12, 13 years has been, given that we've got this new era of computation for everyone, the machinery for that, how can we step up the human and sort of the, you know, to make use of this? That sort of sounds paradoxical, contradictory even. I think it is perhaps paradoxical. What I'm saying is that when we have better machinery, and this is true in other industrial revolutions, you can just use it. That's the point of the machinery. But actually, to make the best use of it, humans need to go up to the next level. And I think when we look at what's possible now with computation, computational machinery, there's a level we're not getting people up to in their education. And that's really what I want to talk about here. And in a sense, I think it's both for a small number of people who want to be sort of doing these things at a very high level, but it's also for everyone. And in a sense, I'm sort of calling this computational thinking, but I'm never very happy with the terminology. So I think the big question that education has to face, actually has to face across many domains, but in this domain, it's particularly pronounced. You know, the real world is changing, has changed, and it's happening fast. And when you get a change in the real world, how should education react to that change? Should we just kind of ignore it and sort of go on as we were before? Should we, you know, what should we do? And obviously, the rise of computation over the last number of decades has been one of the most dramatic changes in the world's sort of history in terms of machinery. And so it demands a response from education. And the question is, what should that response be and how should it feel? And that's really what I want to talk about. So how has the world changed? Let's just be clear about this. We're in a position now where, at least in most developed countries, most of the time, we have ubiquitous computation. I mean, all of us are carrying around huge computational power, either locally or, you know, through the web, through the internet. And that is a fundamental change from even a few years ago. And it's, you know, it's not going away. It's a change in the world. And, you know, even if something terrible happens in the world, it'll go away for a period perhaps, but it's not going away. So we need to adjust how we think about what you need to learn with that in mind. The other thing to be clear about is high-level computation is now applicable everywhere. So as I said, maths by its nature was centrally in this, and mathematical physics and things like accounting have been around for a long, long time. Mathematics has been deployed on the physical sciences and on things like accounting for a long time. But there are very many things where it is relatively newly deployed in any serious way over the last few decades. And there are other things which are brand new, newly conceived because of it. So obviously, programming is something that is more or less to do with the modern era of computation. Obviously, there was programming before, but in a slightly different form, but fundamentally, the mass rise of programming is that. Data science also, social media and many areas of sort of, you know, high-end finance in this sort of way are newly conceived because we now have high-level computation sort of applicable in many different places or available. Then there are these subjects that are very interesting that have existed before, of course, but now have a computational edge to them. You know, the biosciences, very obvious example. A number of years ago, yes, you could do some basic statistics and things, but you couldn't do anything like as serious as you can now do with different forms of AI or you know, analytics on processes or whatever it is. History and archaeology, I mean, you know, it's a standard thing now to do image processing on archaeological digs. That's an extra dimension to what you would have done before. Medicine, of course, sports, agriculture, marketing, and business are all far more, have a computation applicable in a way that they didn't before. I mean, this is just a little example I sometimes like to give. This is a place where you can just instantly look up, you know, sheep in New Zealand versus people in. Turns out there are more people in the UK than there are sheep in New Zealand. Let's see if this is doing its stuff here. But anyway, so this is just an example of doing an immediate computational query that, you know, just a few years ago you could not sort of easily have done. I mean, it's just like, here it is, the data's here, you can immediately do it, the computation's available, and it's applicable to sort of an agricultural case. You know, here's another kind of thing, so linguistic, what I would call linguistic programming. Here we're finding out what the World War II battles are, and we might now do something like, oh, I don't know, something like a geo list plot, for example, and we could now hopefully try and plot those to see where they actually were in the world. And the fact that they're all in sort of computational form means we're ready to do that. We can look at this piece of history in a sort of, you know, in a fairly sort of computational way. And we might do something else. We might try and say, well, let's, for example, pick out, oh, I don't know, the first 20 of these, and let's, and so there's the syntax in Wolfram language for doing this. Let's just put them on a timeline, for example. So I think we do something like that. We should get a sort of timeline of when those battles actually happened during World War II. So it's not that this replaces a normal way of looking at history. It just gives you another dimension. It gives you a computational history that you didn't have before. It's another way of, an extra way of thinking that, again, wasn't immediately available or available at all in some cases. Here's another example, again, sort of, in a sense, a computational, but actually I always like doing this. So this is picking out from the human genome you know, a sequence of base pairs, and it's trying to look up, okay, so those are all the chromosomes on which that sequence exists and their positions. So the fact that I can sit on my laptop and do that in a few seconds, when it was thought a number of years ago that you couldn't even sequence the whole human genome in a lifetime, is amazing, really, and is a fundamental sort of facet of the fact that we have this sort of ubiquitous computation now available. And another typical example, you know, so I could try and do image detection. Let's see if this works. It's going to be on a different camera, I hope. And yeah, there we go. So my camera over here, and hopefully I'm trying to actually, my screen isn't on here, so I don't know what I'm looking like, but this is a typical thing we're doing with Wolfram language, trying to detect me and to try and put an expression on it and to try and understand what we're doing, and then to try and use interpretation of that down here to make that sort of work. So that's a typical example where many people wouldn't understand in the past that sort of computation could be deployed to recognize images. Now that's a much more prevalent type of thing. So, by the way, the way I did all of those is this Wolfram language thing, and the sort of thing we try to do here is not only build a programming language, but a sort of representation for all of computation. That's been the big driving force for our third of a century, which is, can we represent anything you might want to do computationally, including data, including a notebook front end, including graphics or sounds, whatever it is, can we represent those all in one type of way with a symbolic representation? And that's essentially what Wolfram language is trying to do. And in a sense, WolframAlpha was a way to represent sort of, you know, data and the structure of data and an ontology in the symbolic language, which sort of meshes that with the functions that we have. And that's sort of the way in which that's built. And there's a third thing, which is, can we also have the language sufficiently literate that to some extent anyway, it's sort of human readable. It's a human, sort of rather human communication language. So if I want to write down, and we do this often inside Wolfram Research, if I want to write down an idea to you, a technical idea, can I write it just a piece of Wolfram language code? Because it's sufficiently close to the idea I'm trying to represent that it's a rather efficient way just to write it down and completely precise. So that's another facet of what we're trying to do, which is why I've put the 3 wolves up there, because I feel like we've it's sort of like a I used to call it a triumvirate, but triumvirates didn't work very well. So I think it's the history of the Roman Empire. So triumvirate's the wrong thing. A trio, I think, would be a better way to describe it, of facets that we're trying to do that. And just to show you a typical thing in this that one might, by putting together sort of knowledge and programming and other things together. Let me see if I can do this in real time, though. It's always harder to write code when people are looking at you, so to speak. But what I would like to do is fire up an image of myself and then block myself out with a rectangle. So what I might do is something like, I'm going to show myself. So I've set the current image. So that's what will represent what's on that camera. And now I want to show me, let's say, graphics of a rectangle, let's say, and I want to apply that to finding my face on me. And let's see whether I've done the right thing here. And hopefully, there we go. You can hopefully see that I managed already to block myself out. So perhaps a little bit early to do that in the talk. But that's a typical piece of code. And that's what's kind of nice about wiring all these things together, that you have the algorithms ready to use, and it's kind of like fast to write things. And you can kind of see what's going on here with a little bit of understanding of code and how this works. So when we talk about computation, it's very difficult to find the words here. I think of computation as encompassing many different areas, this very general construct. That's what we thought about with Wolfram language. In a sense, this process we have for getting answers in a very precise way. And there are clearly several sort of subfields of this that one can refer to. Coding, I would count as one piece. I wouldn't call it as a subfield, and I'll come back to how I see this fitting into this bigger picture. Data science is clearly something that is a subfield, if it's not the whole picture. And one of our difficulties in education is I think people sometimes narrow this down more than they ought to in thinking about what the core subject ought to be. So I'm going to argue that there is a core human skill that we need, and I'm going to call it computational thinking for the moment. And when of course, the introduction of coding into the UK and other places is a positive step for sure. It's still quite a small subject. The big computational subject that takes up a huge amount of curriculum time everywhere is maths. And you'd assume maths was therefore doing at least a good job in what I'm going to describe as computational thinking to equip us for this world. And I'm going to argue that the picture isn't as rosy as that. And in fact, we need to make some very major changes. So I'm going to address it about maths, but I don't really care whether we're coming from a maths angle, from a coding angle, from any angle. All I want to see is one mainstream subject that sort of sorts this out for our students. And I don't want the name to get in the way of what we're trying to do. So some sort of opening questions. Is maths and coding education achieving data literacy, data science? Is it promoting logical thought? Is it optimizing economic results and jobs? Is it developing this computational thinking thing? And I'm going to argue, I think it's about 80% the wrong subject. And certainly when you get beyond primary, late primary education into secondary, I don't think it's just that we have teachers who don't teach it right. I think that what they're trying to teach is mostly wrong as a core computational subject for what most of our population needs most of the time. So it's no good blaming teachers for doing the wrong thing. I think it's the curriculum that's largely at fault. And let me describe this. To put it in sort of one sentence, this is it. The difference is, in the real world, in the last few decades, computers now do almost all the calculating, when maths or computation is deployed. In educational maths, people do almost all the calculating. That's the problem. And it's kind of like, however well you do the wrong, however well you get the people to do it, they can't compete with what's happening in the real world. And they're not set up right. And you might think, well, that doesn't matter. You need people to do it first. And I'm going to describe why I don't think that's the right approach. So that, in essence, is my argument as to what's wrong. That's this 80%. Next question, is it right to have everyone think of doing some subject, maths, computational thinking, whatever you want to call it? And I'm going to argue, yes. There are 3 good reasons why maths is a mainstream subject, or the right maths should be. Technical jobs, so increasingly prevalent in our economies. What I call everyday living, just surviving in a modern or even less modern economy, requires a much greater understanding of computational thinking than it did. And we'll come back to that. And what I would call logical mind training, and by which I mean, even if you're not directly using maths or computational thinking, or you're not directly using the actual algorithms or anything like that, the ability to train yourself to think in a way that helps you make decisions. And there are many subjects that would lay a claim to this. Maths itself would lay a claim to this. So I think the claim is rather poor at the moment in much of what we're actually practically doing in secondary education, particularly. Philosophy, various other subjects also have facets. This is not exclusive to this, but these are things that you would hope that we are training in having everyone do this subject. And the other thing I think it's useful to think about is the levels. There's a value add level. People who are doing, top jobs increasingly need to be computational. Then at the other extreme, there's sort of a survival level. Honestly, if you don't understand anything about how to, just day-to-day things, mortgages or, discounts or, risk, any of these things, you don't know anything about, it's really hard to do well or even survive well in a, your life expectancy is probably lower in a modern economy if you really don't get any of that. And in the middle is something which I would call subsistence. Can you hold down a decent level of job, even if it's not a technical job? What facets do you need for that? And we'll come back to this idea of literacy and computational literacy. You wouldn't hire somebody to do a job now who couldn't read and write. What are the computational literacy requirements of the future just to do a normal job, and particularly a management job? So at the center of what I think of as maths and computation is the process. And I think of it as a 4-step process. And you can argue with this. Many people have come up with different ways to describe this. But when you say you're doing maths, basically, I think you're doing 4 steps. You are taking a question that you want to get an answer to, and you're defining the question. And often when I give talks that are in real rooms, I say things like, a question could be, if I talk for too long and we lock everything down, and I put some parameters on it, like we turn the ventilation off and everything, how long could people survive in the room? That might be my defining question. So the next step is you're abstracting it. You're saying, okay, I could just talk about this in English, but I'd like to do much better if I turn this question into an abstract mathematical form, because over hundreds of years, we've developed this fantastic way of representing precisely ideas. And we've also got a fantastic way to transform the questions to the answer, with huge amounts of so to speak, logic to allow us to do that in a meaningful way. And so the second step is set up the question in a precise way. Now, of course, this is a major join with coding, because in the modern world, how do you set up the question? Well, you could write it in nice old mathematical squiggles, but actually that mathematical notation doesn't really cover algorithms very well. It covers expressions, but in algorithms in many cases. So you really want to write this as code. That is what you want to do. You want to be abstracting to code. And that's for 2 reasons. Firstly, because you can represent a much wider range of ideas. And secondly, because step 3, the magical step of taking the question to the answer in an abstract form, is sort of this key step that I'm arguing about as to who should do it, so to speak. And so that's the step, of course, we can now do on computers very, very effectively. And that's another reason, obviously, for having it in code, because it's ready to execute. And then step 4 is you take the answer, x equals 3, and you interpret it back. Does that mean 3 hours in my earlier example? Is that right? Is it 3 hours for everyone? Or somebody is maybe diabetic, and so actually their limiting factor is different from somebody who, it would run out of oxygen early or whatever. So these are ways that you then interpret and think about the problem, and it may not be the same answer for everyone. The problem we've got right now is that we're spending a huge fraction of our mathematics education time on step 3 by hand. And the effect of that is to drown out much of the other steps, and to deploy the thinking on much simpler problems than we should be getting our students to think about, much less messy problems. So we should be using computers much more for step 3 on harder problems, and we should be using students much more for steps 1, 2, and 4 on much more real-life messy things. And that's how I would like to see, in a sense, the curriculum reformed. And in a sense, this process is an iterative thing. So, you're going up maybe multiple times around this process until you get an answer you consider is a satisfactory answer for the question you asked. That's what the process does. And that might take a few seconds. It might take years, depends what you're doing. And, it's interesting because in schools, most people would have to learn how to solve by hand this linear simultaneous equation. And, it's an equation. That's a very useful tool set to know of the existence of. But the details of how you solve this, well, people know usually how to solve linear ones. Sometimes they usually get to quadratic. But, I only have to type something with a third order in here. And most students, after years of schooling, have no idea how to solve that. And I can do it in, a second or less on my computer. So what we got to focus on is the tool sets we need, how you interpret this, how you use this, how you don't get fooled, not mimicking what the computer does best and, pretending to be a computer. And, what's the point? I mean, we've got here something that's done by a computer, which after 10 years of most people's maths education, they can't do. So let's not be bashing their heads against this particular wall. Let's have them working on something that that they can do, and they can step a level up from the computer. And you see this also in how maths is organized. So sort of typical education headings today are about the mechanics inside much of the time: completing the square, inverting matrices, simplifying surds, a thing I particularly hated, etc. What we should be focused on is actually contextual problems needing the whole process. Don't learn some piece of maths, don't think, okay, let's do 20 questions on matrices. Wonderful. So then the next problem you've got about, what's the perfect password for your login? Do I use a matrix for that? Oh yeah, because I just did stuff on matrices. That's completely the wrong thing. One of the difficult things in the modern world is there are thousands of algorithms to choose from, many, many approaches, many different computational ways to do things. It's difficult to choose the best one for the job. That's part of the training you need, what to choose. So, I mean, this is a typical, set of context that I think is, perhaps engaging for some of our students. Most 7-year-olds have a problem of stopping their friends breaking into their stuff. What's a good password? What's a bad password? One we tried with the project we did in Estonia, am I normal? Can computation help me figure out what normal means? It's like my foot size is bigger than somebody else's foot size. Does that make me, more unusual? I mean, can computation help? Much harder problems. Should I insure my laptop or not? Is it worth taking out insurance or not? If I have a game, how many controls do I need? And what's the best basis set for the controls, etc., etc., etc. How many levels of friends am I separated by on Facebook? What's a beautiful shape? These are all relevant questions, but they're not the questions you see in today's maths education. They're sort of fuzzier. They're things to which you might apply maths or computational thinking, but which mostly people are not in their education because they're not allowed to and because the computers aren't there. So the key point I want to make here, which most governments completely don't understand, if you remove the computer from maths or computation education, you will remove most of the context. Why do I say this? Well, let's see what's happening in the real world. Why is maths or computation thought to be so important in the real world compared to even 50 years ago? Because, as we described at the beginning of the talk, many things depend on computational approach to decision making, whether it's biology or, the older things like accounting and physics, or, medicine or anything like that. And even everyday things like mortgages and things are far more complicated, although possibly slightly simpler in the last week. So the contexts are all contexts for computation that only exist because we have mechanized computation. They didn't exist before computers in any serious way. Because the only thing that's allowed maths to be, a lot of mathematicians hate me for saying this, but maths wasn't that useful for most subjects before computers. It's been unlocked for deploying on many, many different subjects, these much fuzzier ones, because we have mechanized computing that allows us to deploy it fantastically better than ever before. If you remove that machinery, you therefore remove most of the context to which we're applying mathematics in the real world. So you can't teach most of what you do in biomedical research in the maths curriculum because you can't do it. It does the different things, different algorithms, different approaches, just can't do it. So you will remove them. So we end up with sort of billiard balls, questions endlessly, because that's one thing you can do by hand. So it really skews what people are taught to things that were hand calculatable, which is mostly not what's being used in the real world. There's another problem. This different computational tool set really is a key facet as to why it really is a different subject. And there's a very different approach. So in the old world, before computers, the limiting step for most mathematics was step 3. You could set up whatever problems you like, but you couldn't compute most of them because it had to be done by hand. Sometimes that's still the case, but often it isn't the case now because we've got computers and they do a fantastically better job than humans. So actually the limiting factor in most cases is one of the other steps, particularly often step 2. But it also changes your approach, because often when you do problems now, you will set up lots of abstractions and try lots of things in parallel because the computation is cheap. It's the setup and, the getting it wrong often that's expensive. So it's a very different approach to how you decide to go about getting the best decisions out of computation. Another exciting thing is you can reorder for conceptual, not computational complexity. Why do we teach calculus so late? The idea of making things smaller to approximate some shape, I don't think is very hard for many much younger children to understand. They're used to making things very, very small, very, very large. That's a very early developmental stage. Well, the reason we do it late is because the calculating is horrible. Doing integrals is hard. So we decide that until everybody has the algebraic ability by hand to do integrals, we're not going to introduce calculus, basically. And that's a great shame. We could be doing the idea of calculus far, far earlier. Also, machine learning in elementary schools. Machine learning has many, many different levels. There's building new neural nets and there's deploying machine learning on a problem. Deploying machine learning on a problem is a very early stage thing. Why isn't it in the maths curriculum? I don't know. It's an algorithm that's used, a set of algorithms that's used widely now. Why have we switched it out? So here's a typical thing that, I think we ought to be doing in maths. So what we've done here is we've divided half the class into, we've divided the class in 2, and we've told half of the class to toss a coin in reality and note down whether they get heads or tails 200 times. We told the other side of it, and so what I'm doing here is instead we told the other part of the class to cheat by just typing in heads and tails without doing the experiment. And then we've sent the results to the teacher. And the question is, and I've cheated here, I haven't done the experiment. The question is, can the teacher tell with some analysis who's cheated? And the answer typically is yes. So I would say, given that we've only passed 1 of the 5 tests here, it's almost certain that I cheated. And now if I'm a good student, I might say, well, let's not do it by pure cheating. Let's do, let's see what I want to do here, random choice. Let's make the computer simulate the heads and tails and see whether I can actually do better by doing this. And so I'm just going to write a little piece of code here to do that. And I'm going to throw this in. Hopefully it'll accept this slightly different look. And I'm going to now look at the results. And Mathematica did rather well in passing this test. So that was a semi-cheat. But then you start asking the students, how do we figure this out? How come the teacher knew who cheated? And they start coming up with theories. Well, it's interesting. And eventually they say, well, maybe it's to do with the sequence of, what you've done. And it turns out most people too evenly press heads and tails, much more even than happens in real life. You get much longer strings of those typically. But the point about this is the sort of thinking you want for, credit card fraud detection. But we don't have this in maths because they're not using a computer. So they're sitting there doing things, but you wouldn't do this without a computer. This is sort of analysis you do with a computer, and you want to get the computer to do it, and you want to understand how it's doing, and then you want to build programs for doing this. So this, to me, is central to what mathematics ought to be doing, the thinking patterns and the deployment. And it's not. So that's what we're trying to do. What do you actually deliver? So I'm saying we need to change this. What is it that you want to deliver? And we faced this problem, particularly when we did the first one of these in Estonia. It's like, okay, Minister of Education has told us to change this. We have a bunch of teachers, we have a bunch of students. What is it? And so we ended up actually building sort of actual learning materials that we thought could map the curriculum, not the other way around, not doing what's traditionally done in the curriculum, which is let's have a bunch of experts sitting in rooms. I always call them smoke-filled rooms, but I'm sure they're not smoke-filled anymore. Deciding what should be in the curriculum. But the problem with that is what they're typically doing is deciding what was in the curriculum with some perturbation. This is a very big change. So I think we're sort of close to the world experts in knowing how people use mathematics around the world. And even we find it very, very difficult to just prescribe that off the top of our heads. So the best thing we've thought of doing is build modules and things that start with a problem, start with an interesting thing to explore, and try to work back from that as to which bits of mathematics you'd actually use, and then try to cover a sort of wide gamut of that. And of course, we need this directed to modern outcomes. If you look at the outcomes from most countries' maths curriculum, it's a funny old mix. It's kind of like, we want critical thinking. Well, wonderful. But what does it mean? And at the other extent, we want the student to know how to, draw a bar chart so that they can put the axis as this way and that way. Well, fine, but that seems kind of right down in the weeds somewhere. Where's the thing in between this? And that's what we've been trying to work out. And then also, unfortunately, the world is driven much by assessments, and one wants to work out how to sort of tether this to representative assessments. Not my favorite thing, but something that one tends to need. So the sort of deliverables we've been thinking about are modules, are sort of very directed learning things where we're really helping both the teachers and the student, because the teachers don't know what this is. It's a new subject. You can't just say, go teach it. They didn't learn the subject. And so what's the best way to help the teacher? Well, you kind of need to train them, but you can also partly help that by having it seems horrific, right? Here's every minute of every lesson. But actually, many of the teachers we've used this with are quite keen on it, because if they get a bit lost, they can follow it. And if they get what's going on, they can just go down their own direction. And that's great. And then what I'd call guided learning, where we want to lay out some basic things to help the student and the teacher, but they're more like projects. But then you also periodically need to say, well, we've got this problem, and you might just think about it this way. But actually, there's a great area of mathematics that's been built over 200 years for this. So let's tell you something about that area of mathematics. And we built some primers where there aren't materials that sort of well exist for this. And, you'd think, and this is, by the way, done backwards now, because basically we're doing all the primer stuff first. We're doing equations. Here's what you need to know about equations. Here's 10 lessons on equations. If you're very lucky, you might deploy them to something that has something to do with your life. We're trying to go backwards. And that's sort of an important facet for what we're doing. We're also building a new outcomes tree, curriculum specking process, and sort of different assessment types. And this has been going since 2010. And I suppose the byline is we're trying to build a core computational curriculum that assumes computers exist. And it seems obvious, but I'm unaware of any such core curriculum in the world that really has done that. So here's a sort of simple example. Let me fire up. Actually, I forgot to do this. Let me see if I can just pull a module up here. This is the sort of computer-based maths. I think Zoom is interfering here a little bit with this. There we go. Okay. So these are some modules that that we built. So there's a few examples here. Let me maybe pull up. Actually, let me pull up a modeling one. So let's say this was one we did with the Irish actually some time ago, which was you know, how fast could I cycle the Irish equivalent of the Tour de France? And this is the teacher edition of this. So this one has lots of boxes and things in to give teacher direction. I'm not sure this is the perfect layout for such a thing as this, but the idea what we're trying to do here is, you know, what are models and what can they tell us about cycling, right? What is a model? I mean, that's never really covered. The maths curriculum, you often don't find very general things like what is a model. You do sometimes, but not deployed in actual situations. And so, you know, we've got a number of I'm not going to go through this, but, you know, here is an example of, if I pull up a page here, this is the direction for teachers in the orange box. So that doesn't exist in the student version. And here's a model we set up. We just thrown a model out. Here's a model somebody's given you. Very common in real life. You get a complicated model. You don't know whether it's right or wrong. But here's a model of in a sense, of a rider's power. And then there are a bunch of questions underneath here that you might be asked about this to help you understand how to look at this model. So this is kind of like that way round. And then the next thing here, you know, further down, it's like, you know, can we now build a model which includes air resistance, for example? So, you know, here's a horrible looking equation. Don't know how to derive it. Maybe I don't know what it does really. Can we use this equation by looking stuff up? Can we somehow deploy this onto our problem in a way that lets us, you know, build something that makes us simulate air resistance? And then, you know, can I do image processing on myself to figure out where different riding positions and whether they actually affect significantly how fast I can ride round different areas of the course, et cetera, et cetera, et cetera. And then can we, you know, load in a Google Maps representation for where I am? I'm not sure where that is in this, you know, actually simulate a route and try and work out how fast I'll actually go around it, et cetera, et cetera, et cetera. A bit of sort of code to go along with this, sort of assisted code. So this is quite a complicated module. This is quite a high level one. But this is the sort of thing, you know, this is a mesh of sort of mathematics, you know, data science, modeling, coding, you know, all of those things meshed together as I think one wants in a sort of real world. So this is what I would call a very guided sort of module. And another sort of thing of these projects, you know, how can you model hurricanes? And it's quite interesting to think of what the sort of human and what the computer should do in all of this. And these are some other things we've been building, a sort of project site. This is where you have a less structured form. You know, how could you model voters and what they're doing at Brexit and so forth? Whatever it is you want to do, something that's a more open-ended use of computation. Again, you don't see this much. So, as I mentioned, we want the right outcomes. And you'll find this on our website. This is an 11-dimensional sort of tree of what we think are sort of high-level outcomes required from a core computational thinking curriculum. And, you know, to just roughly, you know, there are big headings like confidence to tackle new problems. I think we can help to give, you know, if you don't have confidence to tackle a new problem, well, you may as well just learn by rote what to do, because you can't really apply it to a new problem if you don't know, if you don't have the confidence. So there are things you can do to help people get confidence. I think there are very practical things. It's not just magic. You know, instinctive feel for computational thinking. You know, if somebody tells you that, as indeed senior bankers were told, you know, maths has eliminated risk, you should smell a rat. You don't need to do the calculations in great detail. Something doesn't sound right about that. And you need to have a general feeling that it doesn't sound right. You know, if somebody says in physics, I built a perpetual motion machine, same kind of thing. We need to build that understanding, people. You know, if somebody says this causes this, chocolate consumption causes Nobel Prizes, because if you look around the world, it seems like countries with more chocolate consumption per head have more Nobel Prizes. That doesn't smell quite right as an explanation. So that's sort of a thing we need to build into people a lot. And then there's specific critiquing and verifying, generalizing, communicating, collaborating. These are all much more general things than you'd see in a traditional maths group. And then they're the actual, defining the question, the 4 steps we talked about, the detailed algorithms and concepts you need to know about. But each of those you need to know about different levels. You might need to know machine learning is available as a tool without knowing how to derive it. Those are very different levels of things. And computers put that automation level in between and mean that you can have a much wider range of things without actually understanding this, et cetera, and managing computation interpreting. So those are some of the things. And just quickly, the outcomes must engender sort of AI age thinking. What does thinking mean in the world of computers? Well, I think I define thinking as the bit the computer isn't doing. Right? There are many different definitions of thinking, but I think it's a useful working thing. If the computer's doing it successfully, you don't need to be doing that bit. You need to be doing a different bit. So there are various parts of this that I think are very important. We want people to be thinking, and we need to abstract out those thinking techniques and intertwine the creativity in the process. So much in life does really well when you have a process that you tether some creativity to. And I think we can do much, much better at that. And so, if you put the whole picture together, it's a complicated thing. It's like we've got problems and we've got different sort of grades. And as you got the grades, people need to learn more of the different outcomes, and they need to learn them sort of, as you're going up the process in different ways and how to deploy this. And then they may be deployed in different rooms. It might be a context of a sort of a finance room, or it might be a biology room or something. So it's quite a lot to put together to make the curriculum kind of really work. And it's quite complicated to structure that. But linearly writing it down the list, as traditionally happens, I don't think it's going to work very well. And we started to try and map out, in which grade would you have which kind of outcomes appearing with which kind of concepts and so forth. And it's a somewhat, I'm not saying this is a done deal. This is a very early sketch, but it's a slightly complicated picture to try and get to that. I've overrun a bit, so let me just quickly, I'd be interested to hear questions and comments, rude remarks afterwards, objections. I think there are a whole bunch that are leveled at me. I think probably the most important that people come up with first is, don't you need to learn the basics before you learn, something fancier? And my point is, basics of what exactly? The basics of doing hand calculating is not the same as the basics of doing mathematics when you have in an era of computers. And I think there are basics. The 4-step process talked about are key basics, but they're not the same thing. So that's something we can come back to as a theme, if that's useful. Also, a mistake people make is they confuse pedagogy with subject. There are many things we can do with computers to make the learning process better. But don't confuse improving the learning process, whether that's for history or English or maths, with changing the subject because of how the subject in the real world changed. Both are needed, but the subject change is what I've predominantly been talking about. And my book is really an attempt to lay out more than I can in a 40 or 50-minute talk, from what is the whole problem here to what's the fix we're really proposing, to what's the politics, or some of it anyway, in trying to actually achieve a change in a wide-scale way. So if we do what I'm wanting to do, what do we really achieve from this? Well, a few things. I think we can achieve first-rate human problem solvers, not what I think we're sort of, in a sense, achieving now, which is third-rate human computers. Don't get the human to compete with what computers do best, because they'll lose. Get them to work a level up. And another part of this that's critical in the future is optimize the sort of human-computer working relationship. And that needs learning. I mean, just like learning to manage people, learning to manage a computer isn't straightforward. And, we want hybrid decision-making, and we want people on top. We don't want the AIs running it. We want the people running it. So that needs some thought in how we actually educate people for that. Just like it's not trivial to manage other people as a standard problem. You know, the textbook doesn't tell you how to manage a company immediately. I can tell you that. What else can we achieve? I think this is critical. I think we have increasing disenfranchisement across society because of a sort of computational divide. We've got a smallish number of people at the top, you know, the computational top of society who really understand this stuff quite well. They increasingly are, in a sense, in charge of the decisions being made by everyone, because most of the population don't really get enough of what's being discussed in enough detail to really partake in that decision making. And that's a real problem. And I think we've seen some evidence of that problem in the last decade or two, particularly the last decade, in some of our democracies, where the decisions are apparently being taken on a very computational base. But actually, most of the population ask very silly questions about that because they really don't have the basic understanding of how to interact with that computational decision-making process. So we need to achieve this. We need to break down this computational divide and achieve a sort of computational knowledge economy that goes a step beyond what we've had. And a bit like, you know, happened before, and I'll come back to literacy. It's the same kind of issue. When most people couldn't read and write, a small number of people were telling them what to believe, basically. And that's a bad situation. To fix this problem, we got to understand it's an 80% problem, not a 10% problem. Little marginal tweaks here and there isn't going to get us where we need to be. And we've been trying to write down what is the thing that we could all agree on, because the reformers are divided and the people who want to keep the same are often together. And so we tried to develop, and find in my book, a sort of, you know, campaign for core computational curriculum change. And this is sort of what the listing is here. So to leave you as a sort of final thought here, I do think it's useful to compare the movement for mass literacy from the early 1800s to, or the early to mid 1800s, to mass computational literacy. There are similarities. I mean, a lot of people thought it wasn't possible for most people to read and write. It wasn't necessary. The average person was too stupid, whatever it was. And I think that it's been one of the most empowering achievements of mass education. This idea that most people can read and write, it's now sort of enshrined as a worldwide right. And I think computational literacy, in the way I'm describing, needs to head in a similar direction. We need a bedrock of understanding that most people can follow, and we need to move before that. But maths is not doing that right now in the way that I've tried to describe. And so we need to enter a sort of new era of computational enfranchisement. And I think we had some topics I was going to leave you with, but, you know, I've put UK can we lead, but don't just take the UK. There are people from many, many countries here. I hope that wherever can lead first, and sadly, I don't think that's necessarily the UK, will lead. What we need is a set of jurisdictions that really want to pursue this. It's quite hard to do. It's a mainstream subject. It's quite hard to make this happen. And those jurisdictions, I think, will leapfrog others, I have to say, just like Britain did quite well in the early 19th century for that industrial revolution, by having people start to learn to read and write and things like that, and having a mass education faster than many other countries. And that was a major empowering factor for the UK's setup. So thanks very much indeed. Sorry I went on a bit longer than I had intended.
Oh, please don't apologise in the slightest, Conrad. Let's all show our appreciation to Conrad for a fascinating talk there. You can give it some jazz hands or use the reaction emojis on Zoom. That is absolutely fine. Thank you so much. Lots of appreciation there for what you've just shared with us. Thank you, everybody, for joining us, and thank you for your attendance and your excellent participation and questions this evening. Please do fill in our survey. The link is on the screen now, and let us know what you thought of this evening. We do read the feedback. It's not just one of these surveys that we ask people to do by rote. We do actually look at the answers and people's suggestions, and we iterate what we do based on the feedback that we get. So if you have any thoughts about how we can do things in a different way, or what you'd like to see in future seminars, please fill in the survey, and I promise you the answers will be looked at. Now, our next seminar that we've coming up in November is going to be on November the 8th, and that's going to be on the topic of computing education in non-formal settings. And our speakers, we've got a duo next time. We've got our very own Tracy Gardner and Rebecca Franks from the Raspberry Pi Foundation, who spend a lot of time and thought on writing non-formal projects for children to learn all kinds of coding and computational skills. So we're really looking forward to hearing from them in November. And for now, that's the end of the seminar today. If you'd like to give your thanks one more time to Conrad and think about the things that we've heard about this evening. I think this is one that's going to certainly stick in my mind for quite some time. There's going to be quite a lot that I go away and think about as a result of this evening. So I'm really, really grateful for people who give up their time to sort of provoke our thoughts and stimulate our thinking in this way. So thank you again, Conrad, and thank you everyone for coming, and we'll see you in November.